But essentially, the reaction times are predicted by the congruency condition and the target color, their interaction. And here we all include a random intercept by subject. We don't explore more complex mixed models for one simple reason: it takes longer to compute. But everything that we say here also holds if you have a complex random effect structure with nested random factors. That's not problematic. So we first fit this model. You can just you can just copy paste this code. So, okay, this one we can forget about it. Okay, so simr. To fit this model, so we have now we can ask for a summary. A summary of model 1, and we can see that. Oops, I need to make it a little bit smaller. Okay, so we see that for example, we do have only a variance of our random intercept, which is 72.15. That, for example, would be a number not very easy to guess. What is the standard deviation of reaction times across subjects? Well, you can try to guess it. Then we have the intercept, so meaning that I don't remember which color could the target assume, but let me check. Could be red or green. So if in the case in which the congruency is 0, so in an incongruent situation, and when the color of the target is green, your estimated reaction times is about 400 milliseconds. When you have a congruent response, you have a expected reduction of about 30 milliseconds, and another reduction of about 6 milliseconds, which is not significantly different from 0, if your target color is red, and there is no significant interaction between these two. So that's our mixed model. Imagine that we collect this data, or we got this data from another person, okay? And we want to know the power that we had to detect a simr effect with the current setup. So imagine that we want to replicate this study exactly with the same sample size at the level of participants and of trials, and we want to know the power that we would have. Okay, this could be also seen as observed power analysis. So you could also use that to say, well, I had 80% of power to detect the effect in this condition. If that would be, of course, wrong. But we start from that because it's a simple, it's the first thing you need to do with simr. So to do that, we will use the function power sim, so power simulation. The first argument is a fitted LME4 model, in this case the object model 1. Then we need to specify the test of interest, so the test for which we want to power our study. In this case, it will be the fixed effect of congruency 1, and the method will be a t-test. So we need to specify test is the argument equal to fixed to tell simr that this is a fixed effect, and the parameter of interest is the fixed effect of. It's called congruency 1 because in the contrast, in the regression setup, it considers the incongruent as 0. It called the incongruent as 0 and the congruent condition as 1. And when it summarizes our result, it calls the effect congruency 1. You just look at the summary and you see the name of your effect is this one, congruency 1. So you just copy paste the name. And the number of simulated resamples, I lower it down to 100, it takes a little bit. If you want to do that seriously, you take at least 1000. But we get imprecise results, but at least we get them quickly. So let's use function power sim. Let's make it bigger maybe. And we have that fit equal to model 1. And we have test equal to fixed of, that would be, what is it? Congruency 1. You just copy paste this, put it in inverted commas, and then method equal t. We save this to another object. I don't remember how we call that in the PS1. So power simulation 1. And we wait. Oh no, wait, we wait too long. And we also specify how is it called? And sim maybe. And sim equal to 100. Okay. And then we wait a fair amount of time. Now, what this thing is doing is for 100 times we run the mixed model with the same, it generates data from the mixed model parameters, and then it tries every time to fit, it fits every time the same model. It saves the results of the t-test on the parameter congruency 1, and it tells us the result. So when it's done, also this computer is not very fast. When it's done, it will tell us the power that was achieved. I have it, I think here, I have it pre-computed, so we don't need to wait. So it tells us that the achieved power is about 100% with some confidence interval. I'm not sure how it computes confidence interval, but it says that essentially that our power is 100%, meaning that in each and every run of the simulation, the t-test was significant. And it tells us that the effect size for congruency 1 is -30. It doesn't, of course, tell us all the parameters. But one thing, okay, based on 100 simulation without warnings and without errors, as you have seen yesterday, you can easily get errors like singular fit in LME4. And also it tells us that results may be an observed power calculation. So it might be. And it tells us if you plan to use that as an observed power, please don't do that. So that's the message. Of course, you can use that to plan a new study, and that's fine. That's fine. It's not. It's less problematic. But we may want to plan a new study, but we expect that the facilitation for our new study is not as large as the one that we observed in the original data. What can we do? Well, we can decrease the fixed effect to an effect of the size that we'd like. For example, we create a new model, we just copy anything in model 1 in a new fitted object of LME4, it's called model 2. And using the function fixf of model 2, we can just change the effect of congruency 1. So this is a new model, new mixed model, which is for the rest identical to the original one, but now the facilitation effect of congruency is just 10 milliseconds instead of 30 milliseconds. Then we can explore, we can rerun the same power analysis on model 2 instead of model 1. And again, I won't rerun that because it may take a while, but what we get is a very small output. So let's make it bigger. But if you run that, okay, let's make it bigger like this. Maybe you will miss the last part, but it's not very important. So the power is just 62%, and because we lower the effect size, and so we may not be very happy with this power result. So we can try a couple of new things, like if we expect a smaller effect size, we can increase the sample size. How do we do that? There is a function, it's called extend in simr, and we can extend the model Q. A long subject means modify the number of the clusters. So in this case, I want a new model in which all the parameters are identical, but the sample size is 30. So we're just increasing the sample size in terms of number of participants. In this other scenario, we used the function extend, but instead of specifying along subject, we specify within subject. And within subject means we increase the number of observations within participants, so the number of trials. That's the good part of this package, that you can explore different scenarios both in terms of number of clustering, number of cluster, and number of observation within each cluster. And each time I created a new fitted object, so from the previous one. So this will be a situation in which our effect size is 10 milliseconds, and we have 30 subjects, and this will be a situation in which we have the same 10 milliseconds, 30 subjects, but only 50 observations by subject. I think that the original were like 1,000 of observation by the subject. So we lower the number of observation within each, and we see that when we increase the sample size, I don't remember which one was the original sample size actually. Let me check very quickly. Simon subject length unique. We have 16. So we had 16 subjects. So if we have instead 30 subjects, even if we have only 30 milliseconds, with the same setup, so in terms of number of trials, we have a power of 93%. If we reduce the number of trials within each subject to 50 instead of more than 1,000, our power drops to 8%. So that just to tell you that in mixed models, the sample size is not, it's more complex than just increasing the number of participants or increasing the number of trials. They somehow balance out. So if you increase the number of trials, you may afford to have lower number of participants under certain conditions. But it probably, it depends on the variance you have within participants. So the situation is pretty complicated. There are papers, I think, that deal with this, so tell you exactly, simulated complex scenarios, and to tell you when it would be better to increase the number of subjects or the number of observations within each subject. The good part of this is that you can run your own simulation, so that fits better your personal scenario, the one you're interested in, particularly in that occasion. I won't show each of these like run on my computer because it may take a while, like a few minutes, and I don't want to stay a few minutes looking at the simulation to run. But you can try that on your computer. I suggest you to do so if you have some time, so that you get acquainted with the package. And of course, I only scratch the surface. There are other options in the package. The paper is pretty clear, so this is the reference paper, and they also have a tutorial to use the package under certain scenarios. It works also for generalized mixed models, so for example, you can have a logistic mixed model with a dichotomous dependent variable. It works. It works in more complex situations than the one I showed you. You can also manually specify each of the parameters and build your own models. They do have a tutorial for that. It's just very complicated, not in terms of programming, but in conceptual terms, it is difficult. So, yeah, I wouldn't be able to do that in most conditions. What time is it? Maybe it's a bit late. I have till 10:30, right? Okay, let's. The last one, Okay, let's stop for a second. Is there any question so far about power in mixed models? So, mediation analysis. As I told you yesterday, this one should be, I should remove some of these asterisks from here. So, as I told you yesterday, mediation analysis is problematic for power. Why? Because of the test that we use to determine whether we can reject the null hypothesis. Because we cannot assume the normality of the indirect path, we need to test, we often test whether the direct path is significantly different from zero using a bootstrapping procedure. A colleague, Marie, suggested that you, for example, could use a test specifically on the two elements separately, as this is what Baron and Kenny suggest to do. But be advised that when you, she said if you use this simpler version of the test, you can power the study using, for example, the less optimistic estimate between the two elements of the mediated path. The problem with that is that you are not consistent if you then use bootstrapping as a procedure to reject the null hypothesis. So you are powering the study using a different procedure than the one you plan to use later on to test your indirect effect, for example. So the important thing is that you are consistent. So if you use bootstrap as a test for testing the null hypothesis, it's better if you power the test using the same procedure or a similar procedure. The closest that you procedure, the more accurate the power estimate you get. Of course, there are situations in which you cannot, or it's very expensive in terms of computational time, and then you do what you can do, and that's the best you can do. And it's better something than nothing. In this case, okay, this is a mediation example. This is, I think, the mediation example. I took it from, where is it? Maybe Preacher and Hayes. I don't remember whether this is a paper from Baron and Kenny or original paper, or Preacher and Hayes when they show the bootstrapping for mediation. Well, it's a famous example of mediation. So you have an independent variable, dependent variable mediator. You have the effect of x on m is 0.81, effect of m on y is 0.40, and the direct effect is 0.43. So the mediated effect is just the product of these two, is 0.33. This means, and these are standardized, so what is the interpretation of a mediated effect? It means that for each increase, unitary increase in this case, for the increase of one standard deviation in x, you can expect an increase of 0.3306 standard deviation in y because of m, and a remaining increase of 0.43 standard deviation that is not dependent on m. That's the meaning of mediated and direct effect. So, okay, there is, you can run the Sobel test, which is a test that assumes the normality of this mediated effect. It's available in most statistical packages, but this is not what we are going to do. We will use bootstrapping, and since we typically use bootstrapping for determining the effect of the significance of the effect of the mediated effect, we will use an approach that also uses bootstrapping to build confidence intervals around the mediated effect. We reject our procedure to reject the null hypothesis. In this case, is not strictly based on a p-value, because the bootstrapping procedure gives you only a confidence interval. If the confidence interval does not include 0, then you reject the null hypothesis. If it includes 0, it does not reject the null hypothesis. But it's not, as I told you at the beginning, it's not important. It's not important that you reject the null hypothesis based on p-value larger than 0, smaller than 0.5 or something like that. You just need a procedure that allows you to reject a null hypothesis in some cases. In this case, it is the confidence interval does not include 0. And I like this approach, Schoemann's approach, because the guy did something very, very smart. Because there is a package in R that what essentially does is running a full bootstrapping on the data to build confidence interval at every run. And this thing is done like 1,000 times, and then you can collect the power for a certain specific sample size. Then you can repeat that for all the sample sizes of interest, for example, and explore different scenarios. That's I mean, the literal translation of the procedure I told you before, and it's wonderful. Just that I ran that once when we first gave a course on power analysis. It took like all 1 day and 1 night, and the day before I collected the results. I mean, I slept with my computer, fan going, and that's the problem. So if you want to sleep better nights than me, you can use this approach. It does, I think, 3 very smart things that I think that could be applied to other scenarios as well. So it's not only for mediation that this thing is smart. At least 2 of those things are very general. The first one is, instead of bootstrapping confidence interval, what he did is using the so-called Monte Carlo confidence interval. What is Monte Carlo confidence interval? That are simulated confidence, based on Monte Carlo simulation confidence intervals that, however, start from the assumption that at least the 2 coefficients A and B individually are normally distributed. And this then it uses a simulation, a Monte Carlo simulation, for those 2 separately, and then multiplies them. And this essentially is a key to bootstrapping, but this is quicker. I mean, what it does is it simulates normally distributed data from the coefficient A, the coefficient B, and then it combines them. And this makes all the simulation much quicker. The second thing is, what we will do typically is we want to explore the sample sizes between 100 and 300 in steps of 10, for example. So we simulate 100, 110, 120, blah, 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 blah. That's, we could do that. What it does is, okay, we want to explore samples between 100 and 200. I take random numbers in this range. And then I fit a logistic regression model that predicts whether we reject the null hypothesis on the y-axis, the dependent variable, from the sample size. That's the very smart part. So that you can have a logistic equation regression that allow you to predict whether you will obtain a significant result, the probability that you have to obtain a significant result for each of the sample sizes in your range, even the sample sizes that you haven't directly observed. And the good part is that imagine that you only simulated the sample size, I don't know, 115, only 3 times, so you would have an completely imprecise result in that range. But the logistic regression function borrows information from all the other sample sizes as well. So you get much more precise estimate with a small number of runs. So I found that very fascinating approach. And then the power is defined not as the simple proportion of the successes, the rejection of the alternative of the null hypothesis over the total number of trials, but is the predicted value of the logistic regression for that sample size. Another good thing is it doesn't require any programming because Schoemann created a Shiny app. A Shiny app is just an app that runs R under the hood, but has a convenient interface. So if you click here, you can open the Shiny app. Oops. And then, where is it? Yeah. This is the app, and you can specify a few situations, like you can also have two parallel mediators, two serial mediators, or one mediators. You can ask, you set the sample size and find me the power, or set the power and find me the sample size. You can, if you set the sample size, you have to specify the sample size. If you set the power, you need to specify the power and a range of sample sizes of interest. Sample size steps mean that you vary sample size randomly, but by units or by, I don't know, by 10, 10 by 10, etc. Number of Monte Carlo replicates, number of replicates at the level of power analysis, and then number of Monte Carlo replicates at the level of each single analysis. And that's what makes this kind of computation extremely slow. That you have like 20,000 Monte Carlo resampling for each analysis, and you have 1,000 analyses. So it's multiplicative. Random seed to reproducibility and confidence level of interest. Like this corresponds to a p-value, an alpha level of 5%. And then you can specify the paths, parameters under the alternative. You can either specify correlation, which I don't like very much. So you need to specify correlation between between x, m, and y. Just correlation, not regression paths. Or standardized coefficient for the regression paths. And I prefer this setup. So I have it somewhere pre-computed. What is this? Here. I have it pre-computed, but if you want to compute it, this is quite quick. So you plug in the numbers, and you get here the power analysis. In this case, will be 96% of power will be achieved in this setup with a sample size of 100 participants to detect the mediator effect. So I find this very, very smart and very easy to work with. And that will be all for power analysis and simulation. I think that the most important take-home message I want to give you here is that it's not always possible to compute power analysis with G-power. There are many situations in which this is impossible, but with simulation approach, you can essentially do power analysis with every approach, with every complex, however complex the test. You just need a way to simulate the data from the alternative hypothesis. But yeah, it's easier to find out that than to figure out how to analytically solve the power analysis equation, I think, in many situations.